Welcome back. So today I'm going back to Python, and if you remember in an earlier video I used micropython on an ESP32, I think it was, or perhaps it was another micro, but I'm going to be using it just as a normal language today, and I thought I'd combine it with chatGPT, because chatGPT gives you code, and I thought, well, maybe it can help me with Python. So I'm going to be using the Thonny editor and compiler, the one I used before, which is quite the easy one. It's explained in another video how to install it and so on. And I asked it a control systems question. The question was this. It was much simpler than this, but when it responds, it puts all this stuff out for some reason. So I wanted it to simulate a second order dynamic system with varying damping factors, and to put a unit step input and show the step response for varying damping factors. In other words, to graph it. Now, of course, we can do this in MATLAB very easily. It's just a couple of lines in MATLAB. But MATLAB, if you're not a student and you don't work for a university, can be a little bit expensive. So I thought maybe it'd be nice to do it this way. I mean, everything's free. Being a Scotsman, I think if something's free, then why not use it? Unfortunately, it's not perhaps quite as straightforward as MATLAB, where it's kind of all done for you. But here's the answer it gave, nevertheless. Now it gives you eventually the code. I mean, I'm going to skip past all this. It says here, sure, here's the code in Python. To simulate a second order dynamic system with varying damping factor, display the step response. So the first thing to notice is these are libraries, NumPy, and that's what is it? I've forgotten what it does now. I think it's just a numerical thing. That's all that's. And this is a plotting library, matplot library, and this one's SciPy. And this one I didn't know about. This one actually simulates dynamic systems, a bit like MATLAB, a bit like the step command in MATLAB, which I can go over very briefly. But it means that if you don't have it immediately, you have to sort of load that library into your system, which isn't difficult to do, really. I'll show you how to do that. You see what it's done is, though, it's defined a gain of 2 on the system. Well, that doesn't matter, but it's defined a time constant. The thing about second order systems is, unless they're critically or over damped, in which case they've got 2 time constants, they don't really have time constants. So it's not a very good definition, this, but it turns out it is kind of all right, because it's defined as 1, so everything kind of defaults to 1, and it's kind of all right, but I'm going to change it anyway in my version of the program. It's even defined a time delay, which is going to be 0, and it turns out that doesn't seem to work either. It's put the damping factors into an array, and that's quite nice. And then it's down here. It's defining using the plot command, which comes from matplot library. You can look these commands up individually, for example. It's defining the size, the figure size, and then it's going to go around in a loop, a for loop. And the thing about Python is it's not quite like other languages. You can just pick things out of midair, a bit like BASIC. You don't need to type things like define integers and so on. So he's just defined this thing called damping, which will be an integer in the loop in damping factors. But it won't be an integer. It'll go around an integer number of times, which will be 1, 2, 3, 4 times. Okay, and each time it goes round, it'll pick a different value of the array. So it'll pick 0.1 first, and then 0.3. 0.5 and 0.7, so that's okay. So it's going to go around 4 times, and it's going to plot the step response for each of these damping factors. And you'll again notice more than a passing resemblance to MATLAB here. I don't know whoever wrote these routines probably based them on MATLAB, I don't know. Numerator is that, denominator, and it's defined. Now normally I would define that as, you know, s squared plus 2 zeta omega n s plus omega n squared with an undamped natural frequency. But because everything's a 1 here, it's kind of all right. That's like having an undamped natural frequency of 1, because this thing tau s is defined as 1. It doesn't have Laplace transforms of the way, that's just its definition. It's called it tau s, which again isn't very good. And then it said the system is this thing called from the signal, it's from SciPy, it's got the signal library. And again, like MATLAB, but it's not step as in, well, the step comes later. It just this just defines the system. It would be SYS in MATLAB. So it's signal.transfer function, Newman-Den, these are the two arrays, and it's put a delay in there. Now the interesting thing, if you look at the actual, look this up, you can do a Google for that. You'll find it doesn't seem to have a delay, so I'm not sure where it got that from, the time delay. Maybe there is a version that has a time delay. And this is generating a time vector. Now that's quite useful. So that tells us how many points there's going to be in the this thing that's in the mathematics, the numerical library. So that gives us a vector of time 0 to 10 and spaced out by 1,000 with 1,000 samples. So that should go to 10 seconds. Then again, like MATLAB, it's defined an input of ones, which would seem kind of logical. But again, if you look up signal.step in the Python library, there it is in the SciPy, it doesn't really have a U input at all. It's got the system. This is an initial state vector, which you can put to 0 or anything you like. This is the number of point, the time vector. Gets set to nothing there. There is a default if you don't define it. So defining it actually is a good thing, because otherwise it can lead to a very minimum number of points and not a very good simulation. But it doesn't have a, you see, it gives out the output of the system and the t if you the number of points that it's going to use by default, but it doesn't actually have an input as such. So it just assumes the input's 1, so unit step. So I really not know where it got that from. And then it simulates the system anyway with this thing signal.step, and then it plots it, and it's going to do that in a loop. And then we're going to label it later time, and then going to put a grid on it, and you've got to show it. So I'm going to look at my program now. You'll see it's actually different from the one that's in there. So first of all, I didn't have this thing called SciPy. So this is the Thonny editor, or environment rather. If you don't have that particular library, you can just copy it. You go to Tools, Manage Packages, and just put it in here, which is SciPy. Search for it. There it is. Click on that, and then well, it's in already, but normally it would say install, and you click on install and it's there, and then it's very simple. Its job is done. So I've changed the program slightly. So this is really using ChatGPT as a guideline, because when I run it straight away, it come up with errors. I already explained the reasons of some of them. So I had to take away the delay and so on. If you want a time delay, I'm not sure how you do it at the moment. It's not what I want at the moment. So I have to find a gain KP is 1 and a natural frequency omega n, and I've left the array as it was, time varying. But let's look at the original here. can see I've done something very similar now. This is the same plot for damping and damping factors. It's the same loop again, but I've made the denominator 1 for s squared plus 2 zeta omega ns plus omega n squared. So I've just changed that slightly. There it is. And then I had to, for the system to be created, I just put new denominator. I didn't put the delay part in here because it simply wouldn't take it. Here it says generate the step input. Well, it wouldn't take that either. So what I generated the time vector, which is just 0 to 50 seconds in steps of, sorry, not in steps of 1,000, 0 to 50 seconds with 1,000 steps altogether. If you make that too small, it'll give you a sort of jagged output, which you don't want. This was the input, but I didn't accept it. The signal.step function, which it calls, I just put sys and t equals t. I didn't need the x naught. You can put that in, but it doesn't seem to make any difference if it defaults to 0, and it doesn't accept that at all, and I can't find it in the library at the moment anyway. If somebody does know where it is, they can explain it to me. And then to plot the step response for each one of the damping factors, and does this really neatly actually, and that's it really. So it took me maybe 10-15 minutes of fiddling around, looking at the libraries and realizing certain things didn't work, and then we'll just run it. This little green thing here is called it second order, and there she is. It's really quite amazing. So the damping factor of 0.1, there it is, 0.3, 0.7 and so on. And it's quite a nice output. You can see it's easily as good as MATLAB. However, is it right? So we'll just go to MATLAB and run MATLAB, and I'm just going to run, I'm not going to run all the different damping factors. I'll just pick a damping factor of 0.1, which should go up to about just less than 1.75, and we'll check that it gives us the same answer. So it's got a numerator of just 1, and denominator, actually I have to define a damping factor, call it damp equals 0.1, and the denominator is going to be s squared, which is just 1 plus 2 times zeta, the damping factor, because it's damping factor, times omega n, which is just going to be 1, plus omega n squared, which will be 1 again. Oh, didn't like that. What did I do? Oh, sorry, denominator equals 1, 2 times damping factor times 1, or just whatever, and then 1. I need the 1. I've made a few mistakes there actually. So these are the coefficients, and that's the coefficients of the denominator. Just scrub this a bit. This is obviously nonsense. Then we can either define the system, or we can just do a straight step response. We'll just do step of new denominator, and it should do it for us in MATLAB. And there's the MATLAB solution. Actually not quite as nice, but of course you can color up your MATLAB answers, can't you? You can make it thicker lines and edit them. Quite amazing. So you'll see the time axis is the same. It's gone to 50 seconds there. By that time it's kind of died out. It's got the right overshoot, about just 1.75. It's, I don't know if I can, oh there it is, 1.73 it says there. I can do the same thing here. Again, this is very similar to MATLAB. I can, you see down in the bottom right here, you see the X and Y. It says 1.737 there. Yes, it changes as I move around along there for each of the graphs. And its first sort of oscillation finishes by about 10 seconds it's gone to this first peak, just past the second peak really of this response, and there it is. So clearly that simulation is right, and that's quite a nice demonstration really of ChatGPT and how you can use it to help your software if you're doing little exercises like that. That might be the kind of simple exercise you might get in a first assignment on something, along with something else, some other part, the second part to it, which you could do yourself then in Python. So you see, I don't need to be a Python expert to use Python, because I'm using the AI as a kind of guide, but unfortunately it's not a very good guide in the sense it doesn't get things 100% right. But that's good from my point of view, because then I can learn from its mistakes and think, well, that doesn't look right, and then I have to look up the function, and I have to find out how it really works. Anyway, thanks for watching. I thought you might like this. Is a slightly different thing that I normally do, but there it is. Bye bye.